Okay, this is going to be our first video for section 1.8, Introduction to Linear Transformations. And so what this section is going to do is it's going to let us look at this matrix stuff we've been doing from a completely different point of view, and that point of view is going to help us understand what's going on, hopefully, in all this linear algebra stuff. In fact, we're still going to be solving system equations. We're still going to be looking at matrix and doing row operations, and it's the same concepts, but looking at it from different points of view. And it turns out by doing that, you can really gain some insights on what's happening. So think back to either calculus or algebra, and if someone asked you, give an example of a linear function, you might answer something like y equal to 3x plus 2. Right? In calculus and in algebra, that's something linear. It's graphs of line. However, in this class, that is not going to be a linear function. Now, to make sure that we don't confuse what the concept is in this class is what you've learned previously, that's why we're not going to call it linear functions anymore. We're going to call them linear transformations. It gives us a way to differentiate between what we're talking about here. Now, the official definition of what a linear transformation is as follows. A function, and we're going to call this, say, I don't know, t, from some set v to some set w, and v and w here are going to be vector spaces. Now, the typical idea here is it might be a function, say, from R3 to R5 or something like that. So we're going to be generally dealing with Rn here. But in general, a function is linear transformation if the following two conditions are true. And those conditions are as follows, that if you are ever adding up two vectors, getting an answer, and then applying that function to that result and getting a new output, you are guaranteed to get the same answer as if you had plugged in each of those vectors separately and then added the two outputs. Secondly, is that if you have a vector that is being multiplied by a constant and then you plug it in your function, then you can instead plug in just the vector into your function, get an output, and multiply it by the constant. So these are the two important properties that you need for a linear transformation. And so let me give you an example of one here. Let's say f of x is 5 times x. So this is a function whose input is r and whose output is r. By the way, we have an official name for this here. The first part you're probably used to is called the domain. The second part is called the codomain. And I do want to make an important point here. The codomain is not the same thing as the range. And we're actually going to see that in a little bit, how they're different. But for right now, at least, those are the official names, the domain and codomain. And we can just check here. If we were adding up two different numbers inside my function, then that would be 5 times x1 plus x2 in parentheses. By the distributive law, we can distribute 5x1 plus 5x2, and that's the same thing as if we had plugged in x1 and x2 separately and then added the results. Similarly, if I take a number and multiply it by a constant c, based on this formula for the function, we'd have 5 times cx. And then based on the associative and commutative properties, I can rearrange this to c times 5x, which is c times the output. And so this function here satisfies these. If you were to check for the 3x plus 2, though, it would not work. And here's an example of this. F of 1 is going to be 5. F of 2 is going to be 8. But if you do f of 1 plus 2, which is f of 3, that would be 11, and that is not the same as if you added up the two individual results. So this shows you that since you get a different answer, this fails property 1. And if it fails property 1 or 2, that means it's not a linear transformation. Now, why don't we do another example here? Let's do one that's maybe a little bit more interesting. Let's do a function which is going to take in an R2 vector and spit out an R1 vector. And this function is going to be of an input x, y. And I'll give myself, I don't know, 2x minus y as my function here. And so let's see what happens under property 1 if I'm adding up two different vectors. So it would be x1, y1 plus x2, y2. Then if you added them first together, you'd have the new vector x1 plus x2, y1 plus y2. And then based on this function here, which is 2x minus y, it would be 2 times the x coordinate minus the y coordinate, which by doing a little bit of algebra here is the same as 2x1 minus y1 plus 2x2 minus y2, which is the same as the function applied to the first point plus the function applied to the second point. So what that shows us is it satisfies condition 1. Then we would check condition 2 here, and that's if I have a constant times an input vector. Well, if I multiply the constant first, I'd have the new vector cx, cy. If I plug that in my function here, I'd have 2cx minus cy. And then we can factor the c out to get 2x minus y, which is the same as the constant times the original function. And again, this shows it satisfies condition 2. And so once it satisfies both conditions, that means f is a linear transformation. So hopefully you've got at least a rough idea now of the properties that we need for linear transformations. And then we're going to go on to the next video and we'll see what are we going to actually do with this thing here. Well, what's the purpose of this linear transformation?